Welcome to lesson 4.6, translations as vectors. So we have already looked at the idea of translations. And translations you can simply think of, kind of in this case, as a slide or a shift. So how can we characterize or represent these slides or shifts using a single vector? And what you can think of as a vector is kind of like a ray, but it tells us the direction and magnitude of a translation. So a quantity that can be characterized by its direction and magnitude, so direction and distance, can be drawn as a vector. Direction described by the ray, and the magnitude is the length that are found by connecting any point to its image. So if we're finding a vector from scratch, let's look at the R and the R here. If this just slid, we could choose any point off the R. So if I chose the point in the upper left, I would have to connect that with the point of the image R in the same spot. And by doing so, I am drawing my vector, which gives me the length from the original point to the new point and the angle or direction of that shift. So a translation vector then is a vector that gives the length and the direction of a particular translation. So if we're looking at what translated A to B, so the translation from A to B could be represented with a vector. And the way that we draw this is, if we're starting at A, ending at B, the arrow would point toward the B. And when we're naming a vector, it looks like the ray symbol, except there's only a single arrow on top. So a vector symbol goes over, and then there's just this little single arrow on top, and then whatever letter or letters would go underneath. So this would be vector V. So this here, vector AB, is the same thing as vector V. They just slid it over. So let's look at that a little bit closer as it states here. So if we're looking at these diagrams, the arrow in the diagram above shows two ways of identifying a translation vector. The vector that starts at A and ends at point B is denoted ray AB. So the ray AB is one way to show this vector. The other, and the point A, called our initial point, B is called the terminal point, where you start as the initial, where you end as the terminal. A half arrow or harpoon symbol above a single lowercase letter or a bold single letter are the other ways to identify a vector. So I could, again, vector AB or vector V, same vector, two different ways to identify or name it. So there's a few ways that we can do this process. Using the diagram below, draw the image of ABC under the translation given by the vector DE. So they gave us original triangle ABC, and they gave us vector DE. I'm going to explain to you how I did the rest of this drawing. The book explains it one way, perfectly fine to do that, although I think my way is a lot easier and more streamlined with less of a mess. So if you want to explore the book's way, it's on page 218, exercise 1. You can see their process. I'm going to teach you how to do the translation of the vector my way. So the way that I do it, the first thing I do is create a line perpendicular to the vector. So it doesn't matter where it goes through the vector, as long as this line is perpendicular to my vector. So meets it or crosses it at 90 degrees. So I just drew and extended that line. I need to extend that line far enough that each of my points, A, B, and C, from my original shape, could hit it if they were also meeting it at 90 degrees. So once we've drawn the perpendicular line to the vector, through each of our points, we're going to draw a line that is perpendicular to the one we just created. So now this line here that I just drew, I want to draw lines through point A, B, and C that are all perpendicular to this line. So that would all cross it at 90 degrees. So what I'd want to do is I'd want to take my protractor, line up the 90 degrees, and then I'd extend each of these lines all the way. So again, the sloppy drawing here, because I erased some, but each of these we'd want to make sure through A, B, and C, that's terrible, through A, B, and C, we'd want to extend those so each of these cross that line at 90 degrees. So we're just drawing in those perpendiculars. So once you have these lines drawn in, and you can see I went back and erased this little part, but I left them going out this way. The reason that I extended them up to the right rather than down to the left is because my vector was going up to the right. So now that I have these three lines drawn, I have the lines that I'll be sliding along. All we have to do now is measure the length of this vector, so the length from D to E, and then we're going to move point A along its line that length. That'd give me A prime. Point B moves along its line the same length. Point C moves along its line the same length. As long as these three lines are perpendicular to this original one we drew, these three lines end up being parallel to our vector. So then all we have to do is shift the points, that distance, and reconnect them. So by doing your first perpendicular line, and then any of these lines perpendicular to that, you're guaranteeing that they're parallel to your vector. So all we have to do is measure the distance and slide the points that same distance and relabel them. So then, and I apologize, part of this got cut off, but what it says here, it's often easier to work with vectors using coordinates. In the diagram at the right, C prime, D prime, E prime, H prime is the image of CDEH under translation by the vector V. And I drew the vector V over here. So original and our final image. You could tell someone how to get from point C, or a point on CDEH to a point on C prime, D prime, E prime, H prime by saying, right 5 units and up 3 units, because the vector on the graph went right 5, up 3. So the vector information is communicated mathematically by writing 5, 3 in kind of these little jagged squared off brackets. So it kind of looks like a line that way, then a line that way. And it'd be that way and that way. So inside of those kind of segmented brackets, we can write the vector. The symbol right here describes how to get from the initial point to the terminal point by traveling first horizontally, so your x value, then vertically the y value. The horizontal and vertical distance are called the horizontal component and the vertical component. So it always goes horizontal, then vertical for the vector notation. So example, using vector notation. P prime is the image of point P, which original point P was at 3, -4, under the translation by the vector -5, 8. So that tells me horizontally, because it's a negative, we're going left 5, and then the vertical, because it's positive, up 8. Find the coordinates of P prime. So my notation could be my original point 3 plus the -5, or left 5 would put P prime at a -2, comma, and then the -4 plus the 8 gives us 4. So P prime is at -2, comma 4. Example 3 says, suppose the translation maps Q at 4, 8 onto Q prime, 1, comma 9. They want us to find the vector that describes this translation. So we're not finding the new coordinate. In this one, we are finding the translation vector. So let's look at the change in the x. We started at 4, went to 1. So that's subtracting 3, moving left 3. So we have a -3. For the y coordinates, we went from 8 to 9, which was adding 1. So that'd be moving up 1, or a +1. So that translation vector, and I didn't do a very good job of making those types of brackets, shouldn't be just parenthesis, should be like that. Our translation vector would be a -3, comma 1. Left 3, up 1. And then we have our final kind of little table here just to summarize some of the different info from our transformations. So types of transformations. A reflection can also be called a flip, specifically determined by the line of reflection. And the way that we get there is it's one reflection. So the description in terms of how many reflections, it's just 1 over a line. What's a rotation? Well, a rotation can be called a turn. It's determined by the center and the magnitude. And the rotation is the composite of 2 reflections over intersecting lines. And then we're going back to what we looked at today, a translation, which can be a slide or a shift. That's determined by its vector, and that's the composite of 2 reflections over parallel lines. So for those that would like another example of this process, I will make another short video walking you through these steps. Otherwise, on the practice problems, just be careful to make sure that you're matching that first perpendicular up with each point carefully so that those are perpendicular to that original line.